This is lecture 20 on the likelihood ratio test. So today we're going to continue talking about hypothesis testing. And last time we had ended our discussion talking about the size and level of a test. So let's rehash that definition real quick. We say a test is, quote, size alpha if we look at basically the maximum probability of a type 1 error, which is the max overall theta in our null set, beta, or I shouldn't call it null set, in our null hypothesis of beta of theta. If that thing is alpha, we say it's a size alpha test. So this is the max type 1 error probability. And so ideally, we'd be able to find a size alpha test. Sometimes we can't. And so what we look at instead is we look for a level alpha test. We say a test is, quote, level alpha if this maximum type 1 error probability is not more than alpha. So again, this thing is our max type 1 error probability. So we've talked about kind of some basic theory, and we've even seen some hypothesis tests or seen some examples of power functions. And today we're going to talk about how do we construct hypothesis tests. Are there kind of general ways of constructing hypothesis tests? And how do we construct good hypothesis tests? And what can we say theoretically about some procedures to build hypothesis tests, how good the resulting test is? So we're going to spend a bit of time today on what's called the likelihood ratio test. And this is often denoted, almost exclusively denoted, LRT. So the LRT is going to be one general hypothesis test. So it's kind of a general form of hypothesis test. And it turns out these likelihood ratio tests, I'll give you the punchline up front, are often very good tests, and we'll talk about exactly what good means. And they are often tests that we are familiar with. So while it may not appear initially, we can often show that in some of the familiar scenarios, these are tests that we're familiar with. However, it's a larger class of tests and includes things that we are less familiar with. Nonetheless, we'll be able to say some nice things about those tests as well. So the likelihood ratio test, the central object of study for a lot of this course, is the likelihood function. So L of theta, we called our likelihood function, which was just a rebranding of f theta of x, right? And it was viewing this joint PDF of our random sample as a function of theta rather than as a function of x with theta fixed. So it's like x fixed, a function of theta given x fixed, as opposed to how we normally think of it as theta fixed and a function of x. So this is called the likelihood function, right? Some recap. And this is really kind of a central object in mathematical statistics. And there's even a kind of a principle, an overarching principle that says that this likelihood function basically contains everything there is to know about our data. And the likelihood principle says that we should follow our nose as far as the likelihood function goes when building estimators and building hypothesis tests and so forth. And so the reason this thing shows up over and over is the likelihood principle basically says we should pay attention to this. So how are we going to use this likelihood function to build a hypothesis test? Consider that we want to test a hypothesis. And our hypothesis is going to be some null hypothesis that theta is in theta naught versus some alternative hypothesis, HA, that theta is in some set capital theta A. This is our general hypothesis test setup. So we want to test this hypothesis. And we're going to do that with the likelihood ratio test. The LRT statistic is defined, so first we're going to define what we're calling the LRT statistic, and then we're going to use it to define a test, which is something that we often do. So we're going to define the test statistic, or the likelihood ratio test statistic. And the likelihood ratio test statistic is defined as, and typically it's denoted with a lambda of x, and right, so it's a statistic as a function of our sample, and you could even make this random if you want. It is defined as the maximum value over the null hypothesis that our likelihood function takes on, divided by the maximum value over the alternative over the whole space that our likelihood function takes on. So this is the max value of L over the null hypothesis divided by the max value of L over entire space. So what is the maximum value that, let's talk about the denominator first, that this thing will take on over the whole space. Well, we could just represent that as L of theta hat MLE. So the MLE, of course, is the argmax, is the value of theta that maximizes this likelihood. And so if I were to plug that back in, of course, that would give me the maximum, the value it attains, right? So the bottom you can think of as just L of theta hat MLE. And the top you can think of L of, let's call it theta naught hat, and typically we drop the MLE. So let's just say theta hat, this is the MLE, and the top is L of theta hat naught ML, where theta naught hat is the MLE over the space theta naught, right? So when you find the MLE, you find it over some set you maximize over, right? So if we maximize over the whole space, we just call that the MLE. If we maximize over some restricted space, maybe a null hypothesis, theta naught, we could call that some kind of restricted MLE. We would, in this case, call it theta naught hat. And so you can think of the LRT test statistic as I find the MLE if I'm restricted to live in the null hypothesis, and I look at the ratio of the likelihood function evaluated at these things. So what this is telling us, so let me back up real quick. Note that L of theta hat, the MLE over the whole space, must be smaller than L of theta naught hat, right? So let's draw an example picture. So here is maybe my likelihood function, L of theta, and maybe my null hypothesis is this part. That's the null hypothesis, and maybe my likelihood function looks something like, oh, I don't know, something like this. Okay? Whatever it is. So if I were to find the MLE over the whole space, that would be the point here corresponding to my highest overall peak, and this value here would be the value of L at theta hat at my MLE. And if I were to find the MLE over just my null hypothesis, so I'm restricting myself to the red here, then my theta naught hat would be the point corresponding to my lower peak here, and the value at this point, L of theta naught hat, would correspond to the value of my likelihood function at that restricted MLE. So you can notice in this picture that, whoops, I have my sign backwards, good thing I wrote it this way, which is that the likelihood function at theta hat, at the overall MLE, has to be bigger than the likelihood function at the restricted MLE. Why? This is because for the overall MLE, I'm maximizing over the entire space, and for the restricted null hypothesis MLE, I'm maximizing over the restricted space. So the whole space contains that restricted space, and so they could be equal. It could be that that the maximum is in. So another situation I could run into. Let me draw another picture here. It could be. So this is, again, my null hypothesis. It could be my likelihood function looks like this, right? In which case, both my restricted MLE theta naught hat and my overall MLE are the same. And so their values are the same, right? So if it happens that my overall peak ends up on my null hypothesis, these two things will be the same, right? And in which case, L of theta hat is L of theta naught hat. So they can be equal, but the overall MLE has to achieve a larger or equal to value of the restricted one, restricted to my null hypothesis. Why? Because you can either end up in a situation like this where they correspond, or you can end up in a situation in this picture where the overall MLE is not in my null hypothesis, so there'll be some value that's maximizes in my null hypothesis that will be smaller than the overall value, right? So basically, if I increase the, it can't be that the MLE in my null hypothesis is bigger, because then that would just be the overall MLE, because the overall MLE can look in the null hypothesis. And so if that was the bigger one, it would just choose that as the MLE. So it's always true that in this case, if we go back to our LRT statistic, lambda, is that the numerator is always smaller or equal to the denominator. So this thing is always less than or equal to 1, and certainly positive, because the likelihood function is always positive, right? So our first note is that interpreted this way, we say that this LRT test statistic is between 0 and 1. And we can interpret this lambda as basically how likely, in comparison to if I were unrestricted to the whole space, how likely is it that I'm in my null hypothesis? So how likely, so interpret this lambda as how likely this null hypothesis is, or maybe we should say this, how likely data is if data is in my null hypothesis as compared to overall, how likely my data is unrestricted. So lambda, which is the ratio of my restricted MLE, or the likelihood at my restricted MLE divided by my overall likelihood at my MLE. If this thing is, so let's say if lambda is close to 1, then this says that that my null hypothesis, the data having occurred on my null hypothesis, is basically as likely as possible, right? Which is kind of like my second case here, so number 2 as opposed to number 1. In number 2, it says, yeah, which is our LRT would be, our lambda would be exactly 1. This would say, yeah, the likelihood my data occurred with a theta, or corresponds to a theta in my null hypothesis, is as likely as it can be. So that would say, i.e., don't reject h0. It says h0, yeah, that's actually consistent. Or if lambda is approximately 0 or as close to 0, then my null hypothesis is, when you kind of in the layman's term, you could say it's not as likely in comparison to other values of theta. That is, there are other values of theta that make a lot more sense with this data than the current one, i.e. maybe reject h0. So lambda is this LRT, has some nice kind of interpretation, where it's basically telling us about how likely our data is given a theta in our null hypothesis compared to any possible theta to take on. Big values mean, yeah, it's about as likely as possible. So this null hypothesis is, that makes sense. And if it's close to 0, that says that's actually not very likely. There are other values of theta that would make a lot more sense given the data that you've observed. So the way you can form a test out of this, and I basically wrote this out, is the likelihood ratio test, the LRT, says, and to define my hypothesis, all I have to do is give you a rejection region, is that my rejection region R, so this is rejection region, says that my region to reject is all those x's where L of x is small. So what we say is we pick some threshold C, let's just say for some threshold value, some threshold constant C, and if, we're going to pick a threshold, we're going to say if my lambda is smaller than C, I'm going to say that null hypothesis is not that likely, and I'm going to reject the null. But if it's bigger than that C, I'm going to say, well, the null hypothesis is kind of consistent with the data we see. We're not going to reject C. We're not going to reject the null hypothesis. So the LRT just defines it as the rejection region by thresholding this lambda. It says, yeah, reject it if it's too small. How small? Well, you've got to choose some threshold constant C. So how do we choose this constant? So some things to note here is that if C is 0, then we're going to always accept the null, right? If C is 0, then we're going to say, basically, I guess you could, for a continuous case, we're never going to reject. We're always going to accept because we're never going to observe, or with probability 0, we're going to observe some lambda that's less than or equal to 0, right? It's not going to happen. It's basically saying we're only going to, we're only going to reject if the probability or the likelihood is exactly 0. So that would be always rejecting. If we were to set C as 1, then we're going to always reject. At least in a continuous case, we're always going to reject. I suppose in a discrete case, you could observe some lambda exactly equal to 1. But if it were 1, then lambda is always less than or equal to 1. And so we're always going to reject. There is no good enough value of lambda that we're not going to reject. And if C is in between, So let's say C is neither 0 nor 1. Then sometimes reject or accept. So we're going to get something more reasonable in between, right? The 0 and 1 are kind of edge cases that aren't reasonable. Really, you want to pick some C between 0 and 1. So some of the time you're going to reject, some of the time you're not. And you're going to choose this constant based on how strict you want to be. If you want to be really strict, you're going to set it to a, let's see, if you want to be really conservative and not accidentally reject, you would set it high. If you want to be not conservative and you want to just reject a lot, then you're going to set it low. And so you're going to have a trade-off between a type 1 and a type 2 error. So let me actually just write that down. Choose C to trade off type 1 and 2 errors. And so you're going to have to choose C to trade off the, your type 1, type 2 errors to the extent that you want to not make a type 1 or not make a type 2 error. So let me write, for example, if C is close to 1, we're going to end up rejecting, let's say, rejecting a lot, for example. If C is close to 1, if C is exactly 1, we're always going to reject. If it's close to 1, then we're typically going to reject, right? And we're going to run the risk of what? A type 1 error or a type 2 error. So if C is really high, so a type 1 error would be when the null is true, but we reject. So we'll have a higher type 1 error, relatively speaking, but a lower type 2, right? If we reject a lot, we're gonna falsely reject more, but we're gonna not, which is a type 1 error, so we have a higher type 1, but we're not gonna fail to reject when we should as much. So we'll have a lower type 2, kind of other things equal. If C is close to 0, so we're gonna not reject very much, then that will help contain our type 1 error. So we'll have a lower other things equal type 1. And the price we'll pay for that is a higher, generally speaking, type 2. Because we're not rejecting a lot. So we're not going to incorrectly reject the null very often because we're not rejecting a lot. So our type 1 error is controlled. But we're going to have a higher type 2 because when the alternative is actually true, we're going to not as often reject in that case. And so we're going to make a type 2 error when we should have rejected even though we didn't. And so that's the game. That's the whole game, is you choose your value of C to make the correct trade-off you want between your type 1 and your type 2 errors. Okay. So my game is to choose C to make correct type 1 versus type 2 errors. And that's going to depend on what we want to do. Typically, what we want to do is we want to minimize a type 2 error subject to a type 1 constraint. So we'll, for example, a level, which is it, leveler, let's go back up here, which is it? a level test, right? So here's our definition of a level test is we can, if we want to, so typically we'll say, okay, I want to keep my test level alpha, but I want to minimize my type 2 error. So e.g. Build a level, I'm supposed to read level, alpha test, build level alpha test that minimizes type 2 error. And so I'm going to choose my C so that it maintains a level alpha test, that is the probability of type 1 is not more than alpha. And then I'm going to try and build my test so that I choose my C so that it not only maintains level alpha, but it will minimize the type 2 error among all my possible level alpha. So we'll get to that in a minute, but that's basically what's going to happen is, and so you're going to be forced to choose a certain C if you say I want to have a level alpha test and I'm going to choose the minimum type 2 error test among all level alpha is going to give us a particular C, as we'll see. Okay, so maybe we'll look at an example here. Okay, example. Let's assume that we observe some data from a normal distribution with some mean theta that is unknown and some variance sigma squared, and this is known. Okay, so I'd like to take a second here and just point out, all right, this feels like a very natural thing to do in this class, all right? Assume some distribution of the data, right? When you take like an introductory statistics class, they teach you the methods, and then they say, oh, and it has this assumption about normality or something like that, right? That's what we're doing right here. We're making a normality assumption. And we're going to derive a test under a normality assumption, and eventually we should talk about optimality or not of the test. But this is starting to approach kind of the intro stats. After how many math courses, we now can get back to the real version of these intro stats tests and talk about them in a really kind of adult way, which is, what are these tests? Where did they come from? What are their properties? And so this is like a classic test where we say, okay, I'm gonna do a one sample test of mean. That's basically what we have here. We're assuming, well, for now, variance is known, and we want to know something. We want to do a hypothesis test concerning the mean. So, for example, we could test, and this is something you would do in intro stats, theta is less than some constant a versus an alternative, which is that theta is bigger than a. So here, theta not, my null set is like negative infinity, or my null hypothesis negative infinity to a, including a, and the alternative is what? A to infinity. Okay? So that's how we would write that notation. And let's do a likelihood ratio test, maybe form a LRT. So let's see, what test does the LRT tell us here? We all know a one sample mean test from an intro stats course. What would the LRT tell us to do? Okay, so let's write it down. First of all, what is the likelihood function for a normal data? So this is a rebranding of our joint distribution of our random sample. Something like this. We know sigma squared, we don't know theta, so all right, so that's our univariate normal distribution, and we take the product of those, that gives us our joint distribution. And what is the LRT? So lambda is L of theta not hat, the MLE restricted to the null over the overall MLE for theta hat. So our whole space, right, our whole parameter space is just the real line, right? That's the union of those two things, that's the real line. And we know, and if we don't, you can derive it, right? We've seen for a normal distribution, we know that the MLE, the kind of unrestricted MLE for a normal, for the mean of a normal, is just x bar, right? That's kind of sitting really nice. We derived that before. And indeed, we've also got a restricted MLE. I believe we did a restricted version, and it seemed really arbitrary to find a restricted MLE. Why would you ever want to find a restricted MLE? Well, this is exactly why I want to find a restricted MLE, because it's used in the likelihood ratio test. And let's see what this thing is. So my claim, and this is a bit hand-wavy, but not too much, that this basically looks like a quadratic. And maybe more to the point is that if I look at L of theta versus theta, it's going to look something like this. So it looks like e to the negative something in theta squared. I.e., this is like, kind of looks like e to the negative theta squared, which is basically just a normal distribution, right? But this is, so it has this bell-shaped. It looks like this. And our peak of this thing, we know, is at x bar. That's what it means to be the MLE, is that our peak here is attained at x bar. And so the overall MLE obviously corresponds to x bar. And so the question happens, what if we restrict ourselves to our null hypothesis? Now, we've written this hypothesis for some constant a. And we didn't really specify what the constant was, but it doesn't matter. There are basically two scenarios that can happen here. So scenario one is that a could be over here. So this is when a is bigger than, or let's say equal to x bar. Okay? In that case, this whole interval is what we're calling theta naught. It's our null hypothesis. And so the question is, what is the MLE of our restricted space here, which is just the left of the dotted line? Well, because the overall maximum is attained in this interval, this is also just going to be the restricted one. So if A happens to be bigger than or equal to x bar, or concurrently, if I grab some x bar and it's smaller than A, then my restricted MLE is also x bar, because it turns out x bar is in my set negative infinity to A, something like that, and so this peak here is in my set, which is basically this portion of the axis, and so that's my restricted MLE. So that's a simple case, right? If the overall MLE happens to land in my null set, my null hypothesis, well, then the restricted MLE is just that MLE. So let's put a box around this. That's the easy case. Our second case is, of course, the opposite. So here's, again, my, that's not a great picture. Let's try it like that, right? So here is x bar, and this is L of theta against theta. It could be that A is over here. So this is when A is less than x bar, okay? So I have some value of A that's fixed in advance. Maybe it's 5, right? I want to test if my null hypothesis test is bigger or not than 5. And so if I measure some x bar, and x bar is bigger, what was my actual test? My test was that the null is that it's less than A, and the alternative was that it's bigger than A. So if I grab some x bar and grab some data, my x bar is bigger than A, then my restricted space, my null hypothesis, is this part. It's kind of this part of the axis. And so what's my MLE? And the restricted. Now x bar doesn't end up in my null set, my null hypothesis. So it's not just it's not that the restricted MLE is also X bar, because X bar is not in my restricted null hypothesis space. Instead, I want to pick the value in this kind of shaded region that maximizes my likelihood. Well, it's the value at the edge here, right? That is my restricted MLE is just A. And we did this example when we did MLEs. That's my restricted MLE. So if, how did I write this above? If A is less than X bar, then my restricted MLE is just A. So we'll put a box around that. So to recap here, is that my overall MLE, theta hat, is X bar. Easy cheesy. My restricted MLE, theta not hat, takes on one of two values. If X bar is less than or equal to A, so let me just rewrite what our hypothesis was. Our hypothesis was HO is that theta, our mean, less than or equal to A, and the alternative is that theta is bigger than A, right? Let's just go back and check that's what we wrote, right? So that's our null space, so that should be right. So our null is that it's less than or equal to A, our alternative is that it's bigger than A. And we said that our restricted MLE is that if X bar is less than A, which would kind of give evidence, you would think, towards the null being true, our MLE is just X bar. If X bar is bigger than A, it doesn't really give a lot of evidence to H naught. In any case, we derive that our MLE is A. And so we wanted to derive the likelihood ratio test statistic, eventually the likelihood ratio test. This thing is L of our restricted MLE over L of our overall MLE. And so this will take on one of two values if X bar is less than or equal to A versus if X bar is bigger than A. And what will it take on? Well, if in the first case, this will be L of X bar on top over L of X bar on bottom, which is just 1. So in the case where X bar is less than or equal to A, our LRT test statistic will just take on the value of 1. That's supposed to be a 1. That's not very legible, is it? Something like that, right? Because both the overall MLE and the restricted MLE are both X bar. Cool. If we are not in that case, then the restricted MLE is L of A, and the overall MLE is X bar. And so we get L of A over L of X bar. So I can simplify this a little bit. Our lambda is just 1 if X bar is less than or equal to A, and is L of A over L of X bar if X bar is bigger than A, right? So notice that if we go back up to our test, right? We wanted to test a null, which is that theta, our mean, is less than A versus the alternative theta is bigger than A, right? Our LRT, the likelihood ratio test, says that our rejection region, let's just says reject if lambda is less than or equal to some value C, right? And we're going to choose our C from basically this unit interval, 0 to 1. Depending on the trade-off we're going to make, and we'll see how to make that trade-off. If we're in the first case where X bar is less than A, okay, just intuitively, our null hypothesis is that the mean is less than A, less than or equal to A. And so if our sample mean is less than or equal to A, do we have any evidence that our overall mean is bigger than A, right? Our alternative, in order to reject, we need to be able to be convinced that our overall mean of our underlying data is bigger than A. Well, if I measure that our sample mean is not bigger than A, I don't have any evidence that our overall mean certainly is bigger than A. And what that tells us is that our lambda is 1, and we're never going to reject in that case because lambda is never going to be less than C. So in this case, we're never going to reject because lambda is 1, and therefore it's never going to be less than whatever constant we choose. And that makes a lot of sense because what's happening is that we're trying to convince ourselves, in order to reject, we're trying to convince ourselves that the overall mean in this data is bigger than A. And so I go and collect some data, and I measure some sample mean x bar, and x bar is less than A. You go, is that evidence that the overall mean is bigger than A? No, surely not. So surely we're never going to reject. In the other case, if x is bigger than A, now we have some evidence that maybe the overall mean is bigger than A, right? We don't know what the underlying true mean is theta. What we do is we collect some data and we calculate x bar, maybe, or we calculate our test statistic, right? And now if x bar, like if A is 5 and x bar is like 5.01, maybe that's enough to reject, maybe it's not. I mean, if it's 7, maybe that's a lot. If it's 30, okay, maybe that's a huge difference and we definitely should reject. So we'll sometimes reject here, which makes sense. At least we potentially have some evidence that, our overall mean is bigger than A, our underlying data is bigger than A, because the sample mean is bigger than A. So maybe it is, but maybe that's just a probabilistic, occurrence. Maybe it actually is smaller than A, but we just randomly drew a sample that happened to read something bigger than it, that had a sample mean bigger than A. So in the second case, sometimes we reject, sometimes we won't, which makes sense. And how often we reject or we don't, it's going to depend on this ratio, lambda, and the constant we choose, C. And that's going to trade off rejecting a lot, in which case, we'll make more type 1 errors, less type 2, or rejecting a little amount if we put a very low C, in which case we'll make less type 1, but probably more type 2 errors. So it's still a bit abstract in this case because what does L of A and what does L over L of x bar look like? But the procedure basically just says we form this, we're never going to reject if x bar is less than A. If it's bigger than A, sometimes we'll reject. And let's look at what that kind of looks like. So we said that lambda is L of A over L of x bar. And so let's look at what that is. We know what L is, right? And I'll just simplify it. It's 2 pi. Well, let's go up, right? So we way back up here wrote what L was, right? And you could simplify this thing. It's like 2 pi to the negative n over 2, sigma squared to the negative n over 2, e to the whatever, right? To the sum of that stuff, right? That's L, right? And so it's 2 pi to the negative n over 2, sigma squared, which we know, to the negative n over 2. In the top case, we can push that sum through. It's the sum of my xn's minus, instead of theta, we're now plugging in a here, right? So it's xn minus a squared. Okay, that's the top. And if we plug in x bar into the likelihood function, on the bottom, it'll look really similar, right? Because the likelihood function looks pretty similar. But instead of xn minus a, it's xn's minus x bar. So something like that, right? So let's see if we can simplify this and make some sense about what the LRT is actually doing. We have some intuition that's related to x bar. Is it? Is it something we're more used to? So let's just cancel some stuff, right? So those directly cancel, right? Easy cheesy. And I'm going to claim that I can simplify that top and the bottom. Let's just expand out the sum and the square a little bit, right? So the top is, well, we have our -1/2 sigma squared, right? And then what else do we have? So it's going to be like xn squared minus 2a xn plus a squared, and then we're going to sum those up. So we're going to get first the sum of the xn squared. Then we're going to have minus 2a sum of the xn's. And then we're going to, of course, get n a squares. So I'm skipping a couple steps, but you can verify that that is the correct form. And what are we going to get in the bottom if we play a similar game? Okay. Ooh, we're going to really similar. So we're going to sum of the xn squares. Cool. And minus 2. Now instead of a, we have x bar. Okay, plus n. Instead of a squared, it's x bar squared. All right, so it looks something like that. Okay, and so we can now start canceling some things, right? So if I have e to the, just as an aside, if I have e to the ab over e to the a, nope, that's not what I want to do. Something like that, right? This is e to the ab over, I'm sorry, it's e to the a, e to the b over e to the a, and I can cancel those, right? So I can basically cancel that a with that a. And I can do this in this form. For instance, that will cancel with that one, all right? And anything else going to cancel? I think that's the main one. We can also write these all on one line. It's like this exponential at the top. So what do we have up top? We have n a squares minus 2a. And I'm going to write this as nx bar because the sum of them is notationally it's simpler, nx bar. And then I can bring up the things from the bottom, but I have to add a negative sign. So that would be plus 2, and this is x bar squared because this is, 2nx bar squared. 2nx bar squared, right? Because that's an x bar, that's an nx bar. That's nx bar squared. And I change that negative to a positive because I'm bringing it up. And then this should be minus nx bar quantity squared. Okay? So a couple more algebra steps here. Like that. So what do we actually get left with? First of all, I can pull it as an n in all of these terms, so let's just pull that n out, right? That seems like a simpler thing to do. I got an a squared minus 2a x bar, and then I have 2x bar squared minus x bar squared, which should just leave us with x bar quantity squared. And strangely enough, my a squared disappeared. Uh-oh. OneNote's having a fit. Don't do this to me, OneNote. Oh, OneNote. Okay. Let's see. A squared. Man, OneNote does not want to be nice to me today. Jeez. Okay, so if OneNote's actually going to behave now, this should be a squared minus 2a x bar plus x bar squared, right? And this is, now we can notice that this thing is just a quadratic term, something like this. So this looks like what? X bar minus a quantity squared. So this is, of course, lambda. Okay, so all we've done here is we've just derived what our form. So the LRT is to reject if lambda, which is this, is less than some constant. Let's call it C. Now, equivalently, let's say if and only if, I could just take a log of both sides, right? That doesn't change. Equivalently, I could just say this is equivalent to this less than or equal to log of C. Okay, so the LRT would say to reject if negative n over 2 sigma squared times x bar minus a squared is less than log of C. And I could keep playing this game. I'm just trying to simplify this test as much as possible, right? So we're getting to something that, well, now it's starting to involve x bars. So that's really interesting, right? So let's move all this to the other side. This would be like x bar minus a squared less than or equal to negative 2 sigma squared over n times log of C. All right, so the LRT equivalently is to reject if x bar minus a squared less than blah, blah, blah. Or equivalently, I could take a square root. And so normally when I take the square root of a square, you have to have absolute value bars. But recall that I can basically ignore the case where x bar is less than a or equal to a, because I'm never going to reject in that case. And so if I want to build a test of telling me when I need to reject, I can ignore this case. And I can just work. We know in that case, the likelihood ratio is just 1. And we're only working in the case where x bar is bigger than a, right? So if it's bigger than a, then if I take the square root, it was just x minus a, not absolute value of x minus a. And so I'll have a square root on this side. And I could keep playing this game one more step. X bar minus a over, and let's divide by sigma over root n, just for fun. Let's divide by sigma over root n. So notice that I could pull, if I divide by sigma over root n, presumably I should just get negative 2 log C on the right-hand side, right? And so my LRT, all this derivation has gone to show that, what did we start with? We started with a case where we have data with a normal distribution as a known variance and as an unknown mean. And I said, let's derive what this weird procedure called the likelihood ratio test is derived. And so we derived what L was. And it said, if x bar is less than a, I never reject. And then we've basically shown, we've just done some algebra to show that it is equivalent to say that the LRT rejects when x bar minus a over sigma over root n is smaller. We have to be careful. This sign should have flipped here, right? We multiply by a negative number. So this should flip. So the LRT would now correctly derive that the LRT says reject when x bar minus a over sigma over root n is bigger than this constant. And frankly, the value, let's just call this C star, whatever. If you recall, the original hypothesis was the null was that our mean theta was less than or equal to a, and the alternative was that theta is, let's say, bigger than a. And what we did is we showed that the LRT says reject if x bar minus a over sigma over root n is bigger than some value C star. And that test makes a lot of sense. I mean, that's basically what you would do in an intro stat course, right? If I want to test if my mean is smaller than some value a or bigger than some value a, what do? Well, you calculate x bar, and you basically compare x bar to a, and you divide through by what's called the standard error in an intro stats course. And if that is large enough, so my normalized version, x bar minus a over sigma root n, is large enough, I reject. So if x bar is more than some number of standard errors above A, we reject. And that makes sense. We were trying to prove that theta is bigger than some value A. So if x bar, this is x bar is more than C star, whatever that number is, standard errors above A. And in InterStats course, that's what you would do. You would say, x bar is more than this many standard errors above that test value, I'm going to reject. That is, x bar is not just a little bit bigger than A, but it's much bigger than A. And so, that is a sufficient evidence to say that our mean has to be more than A, and we should reject the null and say the alternative is more likely. And so what we've shown is that in this case, at least, the likelihood ratio test derives a totally reasonable test that you would have used anyways. And the only question you have to answer now, so what you could say, oh, the LRT is, L of theta not hat over L of theta. Or in this case, you could say, well, just calculate the standard error of x bar in relation to A, and how many standard errors is x bar above A, and if that's sufficiently large, reject. You say that makes a lot of sense. When you say it in terms of LRT, it's a little more abstract, but turns out the LRT is very easy to prove things about. We'll talk about that next time in more detail. But in general, this LRT testing procedure is going to give us reasonable tests that are very good tests. And in this case, we see it's giving us basically back our z-test is what you would kind of call this in an InterStats course. So the one kind of dangling thing here is how do we determine can I spell determine? C star, right? How do you know how many standard errors is too large? Well, this depends on, I want to control for a type 1 or type 2 error. So typically, what we do is you control for a type 1 error, right? That's what you do in InterStats class. And so what you want to say is that we want to make this, say, a level alpha test. We want the maximum probability over anything in our null hypothesis. We want the probability that we reject to be, in this case, we could say a size alpha test. Maybe we want it to be exactly alpha, right? Or you say less than or equal to. And so this is the kind of classic thing you do is you'd say, I'm going to build this test and I'm going to choose my C star so that I'm sure that I'm not going to make type 1 error with more than an alpha probability. And so in this case, it's simple enough. You can basically determine, you can pretty much determine exactly what C star is, right? So what is the probability I reject, right? What we need to do is find the maximum probability we make a type 1, right? So this is max, this whole thing is the max type 1 error probability, which is that if the null is actually true, so theta is and theta not, what's the probability I make the wrong call and I reject? And I want to make sure that thing's alpha. So I want to fix that at alpha, so I'm never going to make more than that error with more than the alpha probability. Well, what do we reject? Here is our criterion for rejecting. And we have this kind of C star that we're free to choose. We'll get it from tests if we choose differently. And if we put in this condition that we want to make sure that the probability of incorrectly rejecting when the null is true is alpha, that's going to actually determine what C star is. So the probability, why am I writing a probability? We have a symbol for this. The probability of rejecting H naught is, of course, the probability that lambda is less than C by the LRT. So for any particular true value theta, this is the probability for that value of theta of that lambda is less than C. And in our case, we showed that this is lambda being less than C is x bar minus A over sigma over root n is bigger than or equal to C star. And so now you see y divided by sigma over root n, or what we will see, which is that I want to figure out what C star is. So, and I want to actually find the maximum probability of rejecting when the null is true. So what I could do is I could say x bar minus a over sigma of root n, and I'm actually going to add a constant to each side of this equation. I'm going to add a minus theta over sigma of root n. I'm going to add that to both sides. Okay, something like that. And notice that this thing here is now x bar minus theta over root n, and that has a standard normal distribution, right? X bar is normal theta sigma squared over n, and so if I standardize it, this thing is standard normal, and so we could rewrite this as a probability that, let's say, z is bigger than or equal a minus theta over n plus c star. And I want to find the maximum probability. So my question is, over all possible theta in my null hypothesis, what's the maximum value this thing can take on, right? Because I want to fix that at alpha. So if you think about what's going on, this z is a standard normal, right? And so it has a center at 0. This is my standard normal. Z has my standard normal. And if we have here my value, a minus theta over sigma over root n plus c star, the probability I'm bigger than that is this kind of shaded tail region, right? So this is that probability. And I want to say, what's the possible largest value that could be? So I want to look at the maximum over my null. My null is when theta is less than or equal to a, right? So I want the maximum probability of standard normal is bigger than, let's do a minus theta over sigma over root n plus c star, right? I want to say overall theta less than or equal to a, that is all theta in my null, what's the largest this could take on, right? And so if theta, what do we want to do? We want to basically push this thing, this value a minus theta, blah, blah, blah. We're going to push that to the left, right? Because that would give us a larger shaded region here. And we're allowed to push that theta to a, right? We can't push it to larger than a, because then that wouldn't be the maximum over a null. But if we push theta towards a, then this thing will move to the left here, right? Because I'm subtracting off theta. So as I push this theta towards a, this thing should get larger. And so this is going to be, if I push this as far left as I can possibly go, this is going to be maximized when a is theta, because this is going to be as small as possible, right? So we want to push this thing to the left. We're subtracting off theta, so we should make theta as large as possible, right? We have a negative theta here. So if I keep increasing that, this thing should go leftwards. The whole value, a minus theta over blah, 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 should go left. It should go smaller, and that will maximize my probability, which is this shaded region, right? So it's maximized at theta equals to a. So let me just write that. Max at theta is a, because that pushes this whole value as far left as possible, increasing my shaded region as much as possible. So I'm going to push theta to be a, that's allowable. And so at theta is a, this is what I would get. And of course we have theta minus theta, which is 0. So the maximum value this can take on is the probability z is bigger than C star. So what's my point, right? We derived the LRT, which had this form, which we outlined here, right? And it has this arbitrary constant C star that we're allowed to choose. We choose different C stars, we're going to get a different trade-off between a type 1 and a type 2 error. So how are we going to choose that? Well, typically what we do is we say, I want to fix my type 1 error at a certain probability. I want to fix it at alpha. I want to say that the type 1 error probability is alpha, okay, maybe 0.05, whatever. And so how do I determine if I'm what C star to choose so that my type 1 error probability is alpha? Well, let's calculate the type 1 error, or the maximum type 1 error. We showed that the maximum type 1 error is basically the probability z is bigger than this expression involving theta. And if I wanted to make this probability as large as possible, I push theta to a. I take theta as large as possible. And so the maximum, the kind of punchline, is the maximum probability of a type 1 error is the probability z is bigger than C star. So how do I choose? So the question we originally wanted to answer is, how do I choose C star to keep the max type 1 error probability at alpha? Well, I want to choose C star so that the probability z bigger than C star is equal to alpha. So choose C star so that z, which is just some standard normal, bigger than C star is equal to alpha, i.e., we're going to choose C star. The typical way it's denoted is z alpha, or at least that's the notation we'll use. But this is purely notation. This is just saying choose C star so that at z alpha, and z alpha is defined as the point at which so let me draw pictorially what z alpha is, right? If I had a standard normal, so a standard normal, z alpha is the point where there's alpha probability being to the right of that value. The point at which alpha probability to right on a standard normal. So if you took like an intro stats course, you would have looked up at a table, you found the reference value, what is it, like 1.64 for, alpha 0.05 or something, whatever it was, you look up the table, right? And so basically you have to look it up in the table, but you choose the value so that I have an alpha probability of being in this tail. This typically just denoted as z alpha, but it's not super important. So the takeaway here is that I choose that C star to be this point here, this z alpha, so that I have alpha in that tail, which justifies, in an intro stats course, that's why you choose that as the reference value. That's the whole point, right? Intro stats course, you look up in your table, oh, I'm doing a one-sided test, right? And I choose my value, oh, I want, alpha to be 0.05, so I choose my alpha according to that table. That's just looking up the value of z alpha, right? Look up in table, right? Or whatever. So the takeaway here, and you can see how complicated this stuff can get, is that my size alpha LRT is just to reject when x bar minus a over sigma over root n, it's supposed to be a square root, is bigger than or equal to my reference value z alpha, which I look up in the table, right? So we've taken a whole semester to rederive what we learned in intro stats, right? But that's where the procedure comes from in an intro stats course, because this is a likelihood ratio test statistic. If I want to test the hypothesis I want to test, which is either that the mean is less than alpha or the mean is bigger than alpha, what do? The LRT says if I want to keep the size at alpha, so I want to control my type 1 error rate to be alpha, then what I need to do is I'm going to reject when x bar minus a over sigma over root n is bigger than this reference value I look up in the table. It's bigger than that tail probability. And so it shows us in a really nice way that what, and we'll talk about more next time, is that those tests you derive in your intro stats course are really, this is where they come from, right? This is why you do this form, because it's basically doing a likelihood ratio test. And we'll see next time that in many cases those are the best tests to do. And this justifies why do you look up the value in that table, because you're basically finding what we're calling here Z alpha, which is basically the reference value in the table in the intro stats course. Okay, so that was quite a lot to digest, and so we'll call the lecture here because we're at about time. But that is an introduction to likelihood ratio tests. Next time we'll talk about properties of these and show that in some cases we can show these are the best things to do. So those tests you learn in the intro stats course are often the best thing to do, and so you can sleep at night that what we're teaching you in intro stats is correct.